Welcome to AI Dispatch, your channel for the latest AI videos on YouTube. If you don't want to miss these updates, please like, subscribe, and share. Today's video comes from Relentless, featuring Ed Mehr, CEO of Machina Labs. His central claim: the stamped metal panel on your car carries a hidden upfront cost of $120 million in tooling alone. He proposes eliminating that cost entirely by treating solid steel like moldable clay and transforming factories into software reconfigurable platforms. This represents a direct challenge to century-old manufacturing economics. We dissect his engineering logic and its implications for industrial infrastructure. Ed Mehr states that the stamped metal panels on a single vehicle model require an upfront tooling investment of $120 million. This figure reflects the industry standard cost for dies and stamping infrastructure. He claims this entire expense can be eliminated by abandoning the die itself. For over a century, metal forming has relied on a fixed principle. Shaping sheet metal requires a massive static mold and a multi-story stamping press to force the material into the desired geometry. This approach locks manufacturers into rigid, unchangeable tooling. A die set for an early Tesla model cost precisely that $120 million figure. Capital expenditure of this magnitude creates an economic barrier that prevents rapid design iteration and limits manufacturing flexibility. Mehr's solution removes the die completely. His method deploys two industrial robots positioned opposite each other, gripping a metal sheet and moving in synchronized motion to pinch and expand the material. The process resembles a potter shaping clay on a wheel, except the medium is aerospace-grade aluminum or steel. Traditional industry experts reject this approach immediately, citing insufficient rigidity in robotic systems and unpredictable material deflection. Mehr counters that rigidity itself is an outdated solution. Rather than applying brute force through massive iron blocks, his system operates as a robot craftsman. The machines read sensor feedback every 4 milliseconds, continuously monitoring how the metal responds to applied pressure. The robots do not blindly execute a predetermined path. They adjust force and trajectory in real time based on material behavior. Metal forming transitions from a hardware problem demanding enormous physical infrastructure into a software problem requiring high-speed sensor loops and adaptive control algorithms. This engineering shift triggers a fundamental redefinition of what a factory represents. Current manufacturing operates on product-specific facilities. Automotive plants produce cars, aerospace facilities produce rockets. Machinery is custom-built for each product category. Mehr argues this paradigm has reached its end. He envisions facilities where the product being manufactured is irrelevant to the underlying infrastructure. Removing custom tooling and replacing it with software-defined robotic systems allows the same production floor to manufacture automotive body panels in the morning and rocket bulkheads in the afternoon. Manufacturing transitions from hardware-defined to software-defined. He references his tenure at SpaceX, noting that despite their engineering innovations, they still constructed entirely separate facilities for different rocket programs. His vision for future manufacturing resembles a 3D printer for high-strength aerospace metals, a generic platform capable of manifesting any physical design without altering a single hardware component. This flexibility extends to factory deployment itself. Conventional wisdom holds that advanced manufacturing demands deep foundations, reinforced concrete structures, and permanent installation. Facilities are built to remain operational for 50 years at a fixed location. Mehr challenges this assumption by designing complete manufacturing cells that fit inside standard shipping containers. He bases this decision on historical precedent. Human civilization is fundamentally nomadic, and technology must maintain mobility. Static factories become liabilities in rapidly changing markets. Containerized manufacturing cells can be transported via truck, installed within hours, and relocated as needed. Manufacturing capacity transforms from fixed real estate into a deployable asset, analogous to server racks that can be moved between data centers. Regarding capital requirements, the prevailing narrative in Silicon Valley and Detroit holds that launching a robotics manufacturing company demands tens of millions in seed funding just to build a functional prototype. Mehr dismantles this barrier with a specific example. His first working prototype, which validated the supposedly impossible metal forming technology, cost approximately $300,000. He achieved this by bypassing the premium industrial supply chain entirely. He sourced equipment from what he describes as a robot cemetery on the outskirts of Detroit, a warehouse filled with industrial robots scrapped by automotive manufacturers. He purchased used robotic arms for $20,000 each, machines that cost $200,000 when new, His reasoning, the hardware body is not the proprietary element, the control intelligence is. By acquiring the physical structure at scrap prices and installing custom AI-driven control systems, he demonstrated that the financial barrier to entry in heavy industry is largely psychological rather than material. This resourcefulness informs his hiring philosophy, which directly contradicts standard practice in specialized technical fields. Robotics and material science typically require experts with advanced degrees and decades of domain experience. Mehr explicitly prefers naive generalists and interns with a bias toward action. His justification: domain experts are often the first to explain why a proposed solution cannot work. When he suggested forming metal with robots, PhDs cited insufficient rigidity and accuracy problems. Interns, lacking knowledge of the supposed impossibility, simply ran the experiments and found working solutions. He argues that in fields requiring multidisciplinary breakthroughs, deep expertise can function as a cognitive constraint. He values immediate experimentation over prolonged analysis. He believes obsessive individuals can acquire new field expertise within 2 years, making hyper-specialized credentials unnecessary during early development stages. His business model challenges the software-as-a-service obsession dominating modern tech startups. Most robotics companies aim to sell machines or software licenses, pursuing high-margin scalable products. Mehr refuses to sell his machines to most customers. Instead, he sells finished parts. This decision stems from a sober assessment of the American industrial base. Tier 1 suppliers, the companies traditionally manufacturing parts for aerospace and defense prime contractors, are often century-old firms operating on razor-thin margins with no capital for new technology adoption. Selling them advanced robots would be futile. They lack the expertise to operate the equipment and cannot afford integration costs. Mehr concludes that modernizing American manufacturing requires becoming the manufacturer directly. He treats his company as an operations entity, not merely a technology vendor, because the existing industrial ecosystem has eroded too far to absorb the technology otherwise. Mehr's decision-making framework exhibits a consistent structure. He ignores socially agreed upon conventions regarding metal forming methods, hiring credentials, and factory architecture, focusing exclusively on physical constraints and software capabilities. As long as the physics permit metal deformation and software can control the process, he treats the impossible as an engineering problem awaiting a solution. If manufacturing becomes as fluid and software defined as his model predicts, the global supply chain may face structural reorganization at a scale not seen since the Industrial Revolution. If you're interested in the video featured in this episode, click the link below to watch the original.